nonlinear systems and enter a world that is unpredictable and chaotic. A world without superposition. The world of nonlinear systems. Let's start our journey with an example. We'll do a very simple nonlinear system, and we'll show how superposition fails. So our system is as follows. Output y is equal to input x squared. We'll put in two inputs, x1, which is a unit step, and x2, which is a step of height 2. And we'll see how this system responds. So, in response to x1, we will find y1, which is a unit step. And in response to input x2, we will find y2, which is a step of height 4, since 4 is equal to 2 squared. And now, we'll do the superposition test. We'll try a new input. This input will be x3, which is equal to the sum of x1 and x2. And we'll want to know, does this produce an output, y3, which is the sum of y1 and y2? If this system was linear, this would hold true. So here is the question of linearity. We have x1 that produces y1, and x2 which produces y2. And now we put in a new input, which is x1 plus x2. That'll be a step of height 3. Will this produce y1 plus y2, which would be a step of height 5? So is this true? Does an input that is a step of height 3 produce an output which is a step of height 5? If the input is a step of height 3, and the system is y equals x squared, then the height of this step, that is y3, should be 3 squared, or 9. So the actual output of this system is as shown in the graph in the bottom right corner of the page. It's not equal to a step of height 5. If the system was linear, the input that is a step of height 3 would produce the output that is a step of height 5. But it doesn't. It produces the output that is a step of height 9. So we do not have superposition, and this system is nonlinear. We'll now show that this is true for arbitrary inputs, x1 and x2. So, x1 produces y1, which will be x1 squared, and x2 produces y2, which will be x2 squared. And now we'll put in x3, which is x1 plus x2. y3 will be equal to x3 squared. Substituting in for x3, x1 plus x2, we find y3 is equal to x1 squared plus x2 squared plus 2x1 x2. x1 squared is y1 and x2 squared is y2. So y3 is equal to y1 plus y2 plus 2x1 x2. That shows you that y3 is not equal to y1 plus y2. This system does not have superposition. Let's now examine a second example of nonlinear systems. So this is our nonlinear water bucket. The only difference between this and the previous water bucket is this one is cone-shaped, while the previous one was a cylinder. So, x is the volumetric flow rate of water into the bucket. Y is the height of the liquid in this conical bucket. And denote alpha as the cone half angle of the bucket. The relationship between input, output, and initial condition is shown at the bottom of the page. So the height of the water in the water bucket at time t, y of t, is equal to the cubic root of the initial height cubed plus 3 over pi b integral from 0 to t of x of tau d tau, where the integral is equal to the volume that has been added since time 0, and b is equal to the tangent squared of the half angle alpha. Let me now contrast this relationship to that we found for the linear bucket. For the linear bucket, the height, y of t, was equal to the initial height, y at time 0, plus 1 over a times the integral. The total response, y of t, was equal to the 0 input response plus the 0 state response. And you could see that those two responses are added together. That's the hallmark of superposition. For the nonlinear system, you note that we do not have this separation. The 1/3 power mixes the 0 input and 0 state responses together. They can't be separated into a superposition relationship. An alternative way of looking at this nonlinear bucket problem is to write its differential equation. And so here it is. Y dot equals 1 over pi times b times y squared, all times x. So at first you might think this is a linear differential equation, except that you note the coefficient is a function of the signal y. And you remember that when we wrote out the differential equations that were linear, we said that the coefficients could not be functions of the signals x or y. So this is certainly a nonlinear system. Now we'll prove that this differential equation is nonlinear by checking it for homogeneity. Let y1 denote the output when the input is x1. That means that the pair x1, y1 must satisfy the differential equation. If homogeneity holds for this system, then input x2 equal k times x1 should produce output y2 equals k times y1. And this pair x2, y2 should satisfy the differential equation. To check homogeneity, we're going to do that. We're going to see if the pair x2 equals kx1, y2 equals ky1 satisfies the differential equation. So we ask the question, does y2 dot minus 1 over pi b y2 squared times x2 equals 0? We'll substitute in x2 equals kx1, y2 equals ky1. Then we'll perform some algebra to simplify and plug in the equation y dot equals 1 over pi b y1 squared times x1. This produces the relationship k squared y1 dot minus y1 dot. And we ask the question, does this equal to 0? And it does not for all values of k. For homogeneity, this would have to be true for all values of k. And therefore, this system does not obey homogeneity, and it is nonlinear. Now let's look at a third example of a nonlinear system, and this is the pendulum. Our input to the pendulum is a force acting on the bob, and the output is the angle that the pendulum makes with vertical. The equation of motion for the pendulum is ml squared theta double dot plus mg sine theta equals L times F. And you notice, because of the presence of the sine theta term, this differential equation is not a linear differential equation. It will not obey superposition. We'll now look at two physical phenomena that result in nonlinearities and that are common to many electromechanical systems. The first is the force exerted by an electromagnet. The force exerted is equal to a constant times the current that flows through the coils of the electromagnet squared. And so the relationship between force and current is as shown at the bottom of the page. We already learned that a relationship between an output and an input where the input was squared was a nonlinear system. A second nonlinear phenomena, which is often found in systems, is Coulomb friction. This is the force that's exerted by a dry surface on an object sliding upon it. The relationship between force and velocity is as shown in the graph on the upper right. Clearly, this is not a linear relationship. If it was linear, if we doubled the velocity, we'd expect to double the force. But here you notice that if we double the velocity, the force remains constant. It should be noted that viscous friction, as opposed to Coulomb friction, is often treated as a linear force versus velocity relationship. In our next lecture, we'll examine the phenomena that can only occur in nonlinear systems.